We are going to start with the 12th chapter, Thermodynamics. Thermodynamics. The word thermodynamics is made up of two words, thermo and dynamics. Thermo means heat, dynamic means movement. Thermodynamics is a branch of physics that deals with concepts of heat and temperature and the conversion of heat into other forms of energy and vice versa. Right? But next we have thermodynamic system or systems, collection of large number of particles having certain amount. This is not time, okay, it is amount, value, amount of value of pressure, volume and temperature is called, it is certain amount or certain value of pressure, volume and temperature is called thermodynamic system. Next we have three types of thermodynamic system. The first one is open system, the second is closed system, the third one is isolated system. In the open system, the system can exchange both energy and matter. So open system can be defined as a system which exchange both energy and matter with its surroundings. Similarly, in a closed system, matter cannot be exchanged, however, the energy can be exchanged. In an isolated system, both the energy and matter cannot be exchanged with external surroundings. So we have three types of thermodynamic system. I have examples for open, closed, and isolated system. For an open system, the best example is going to be boiling of any liquid. If you boil any liquid, both the energy is going to get exchanged and matter is also going to get exchanged. As you boil, it is going to form vapors and it is going to be exchanged. The matter is going to be exchanged, right? So this is an example for open system. Next, we have example for a closed system. If you heat anything using a lid, then even though you supply the heat and it forms vapors, it will condense at the lid. So whatever matter is there, it will stay inside itself. However, the energy is will be exchanged. So this is going to be an example for closed system. Example for isolated system is going to be a thermo flask, where you keep your liquids hot or cold for more than 12 to 24 hours, right? Ideally it should be not getting hotter or colder, but since it is not an ideal system, it is a best example for isolated system. Here in this case, energy and matter both are trapped inside. So if you take any hot beverage, it is going to stay hot for long periods of time, right? So I can tell both the matter and energy will be trapped inside, meaning there will be no exchange of energy or matter. So this is an example for isolated system. Next, we have thermodynamic variables. The variable physical property of system which completely determine the thermodynamic state of a system is called thermodynamic variable. Important thermodynamic variables include pressure P, volume V, temperature T. Thermodynamic variables can be classified as intensive and extensive variables. The variables which remain unchanged for each part of a system are called intensive variables. The example being pressure, temperature, density. The variables which have different values for different parts of a system are called extensive variables. The example being total mass, internal energy, and volume. Equation of state. Mathematical equation which relates thermodynamic variables of a system is called equation of state. This is also ideal gas equation which is given by PV is equal to nRT, where P is the pressure, V is the volume, N is the number of moles, R is the gas constant, T is the temperature. We will discuss laws of thermodynamics. We have three laws of thermodynamics. I'm going to discuss each law one by one. Zeroth law of thermodynamics. Zeroth law of thermodynamics states that if two systems are in thermal equilibrium with the third, then both systems are in thermal equilibrium with each other. If I consider three systems A, B, and C, if if A is in thermal equilibrium with B and A is also in thermal equilibrium with C, then I can tell A will be in thermal equilibrium with C. This is your zeroth law of thermodynamics. Now, let's talk about the significance of zeroth law. The zeroth law helps us in introducing the concept of temperature. Temperature of any body is a physical quantity which determines whether the temperature is in thermal equilibrium with another body or not. When and if two thermal bodies or two bodies are in thermal equilibrium, then the temperatures are equal and vice versa. Meaning, when the temperature of two bodies are equal, say if I take A and B, if the temperatures are equal, T over here is going to be T over here, the temperatures are equal, then I can tell that two bodies are in thermal equilibrium. Similarly, if two bodies A and B are in thermal equilibrium, then I can tell that both will be having the same temperature. This is going to be the significance of the zeroth law. Moving on, we will discuss about heat, internal energy, and external work done. Heat is the energy that is transferred between system and surroundings because of the temperature difference. It is denoted by the letter Q. Internal energy. Internal energy of a system is defined as sum of kinetic and potential energies of particles of the system. It is denoted by the letter U. External work done. Work is said to be done if there is transfer of energy between a system and its surroundings under the influence of forces without difference in temperature. We have sign conventions of work done and heat. If I consider a system and work is done on the system, then the sign is going to be positive. Similarly, if the work is done by the system, the work is going to be negative, taken as negative. Similarly, if the heat is absorbed by the system, then Q is going to be positive. If heat is released by the system, Q is taken as negative. These are sign conventions for work done and heat. Moving on, we will discuss thermodynamic processes. Isobaric process. Thermodynamic process in which pressure remains constant is known as isobaric process. Isochoric process. Thermodynamic process in which volume remains constant is called isochoric process. Similarly, the examples are given over here. For isobaric, it is going to be heating of any liquid using open lid. When the lid is open, the pressure is going to remain constant. This is the example for isobaric process. For isochoric process, when you close the lid and heat it, here the volume is going to remain constant. This is going to be an example for isochoric process. Adiabatic process. The thermodynamic process in which there is no heat transfer involved is called adiabatic process. If you consider a chamber and a piston with insulating walls, if the walls are insulating, there is no heat exchange. This is an example for adiabatic process. Even your thermoflask is going to be an example for adiabatic process. It is nearly an adiabatic process because there is no exchange of heat there. Isothermal process. The process in which the temperature remains constant is known as isothermal process. If you are heating anything and the temperature is going to be constant, that is called isothermal process. Next, we are going to discuss about PV diagram. A diagram which represents thermodynamic process graphically by taking pressure along the y-axis and volume along the x-axis is called PV diagram. So if we have any system in state A and state B, let us consider there is a system at the point A where the pressure is P1 and volume is V1, and this is changing to B where the pressure is P2 and the volume is V2. Right? Now this curve is going to help us in finding out the work done. That is the significance of PV diagram. So the significance of PV diagram is that the area that is enclosed by the PV curve and the volume axis, meaning that the shaded region is going to give the work done by this process. Okay, is that clear? Now, how can we find out the area under the curve? Anyone? Any idea? Area under the curve can be found out by integrating this particular curve from this point to this point. This point to this point. Okay. So I can write the work done is going to be the integral of dw, which is given by the integral of p multiplied by dv, where V is going to be the change in volume. P is going to be the change in volume. So you can write W as P integral of V1 to V2 d. This is going to be the work done. That is the significance of PV diagram. This is where our PV diagram is going to help. Moving on, we have PV diagrams of different thermodynamic processes. We will start with isobaric process. Isobaric process is a thermodynamic process where pressure remains constant. So your PV diagram is going to be parallel to x-axis in case of isobaric process. Similarly, in case of isomeric, isomeric is another name for isochoric process. Thermodynamic process where volume remains constant is called isochoric, or the other name is isomeric. Right? In this case, the PV diagram for isomeric or isochoric process is going to be parallel to y-axis. In case of isothermal and adiabatic, it is going to be a curve, and it is to be noted that always the isothermal curve is going to be on the top and adiabatic curve is going to be at the bottom whenever you consider isothermal and adiabatic PV diagrams. Next, work done by a system during isothermal process. Now we are going to derive the work done for isothermal process. Consider n moles of gas as system taken in a cylinder fitted with a piston. Let the gas be allowed to expand isothermally from state A to state B. So let me consider this point as state A. Let me consider this point as state B. Let the pressure over here be P1. Let the volume here be V1. Here let the pressure be P2. The volume V2. Let AB represent the isothermal process. The work done during this process is given by W, which is going to be the integral from V1 to V2, from V1 to V2, P dot dV, P dot dV, from equation of state, from equation of state or ideal gas equation, I know that PV is going to be equal to nR. PV is going to be equal to nRT. Now, I can take the value of P as nRT divided by V. I can take this as nRT divided by V. Same. Now, this value, the P value can be substituted in this particular equation, right? Upon substituting, I will be getting work done as integral of the function p multiplied by dv from v1 to v2. Instead of p, I can substitute nrt divided by v, right? Multiplied by dv, multiplied by dv. Now, nrt is going to be constant, so I can take that outside. I will be getting work done W as nRT is taken outside. I will be having the integral of dV divided by V from V1 to V2. There is a direct formula for this. The integral of dx divided by x is given by log of x. It is given by log of x from, if it is from a to b, it is going to be from a to b. This can be written as log b minus log a. Similarly, using the same, I will be getting over here w is equal to nrt log of base e. This also can be written as log of b by a, log of b by a. Now, similarly, taking b and a, in this case it is v2 and v1, I'm going to get log b by a, which is nothing but v2 divided by v1, v2 divided by v1. Now, in this case, we have log of base e. Removing this base e, I can multiply the same with a constant, that is 2.303 nRT log v2 divided by v1. This is going to be the work done in case of isothermal process. This is one of the formula. One more formula I can write from here. I know that P1V1 is going to be equal to P2V2. Substituting or taking P to one side and V to one side, I can write this as P1V1. P1 divided by P2 is going to be equal to P2 PV2 divided by V1. The same can be substituted over here. And now, another formula for work done is going to be 2.303 nRT log V2 divided by V1 can be written as P1 divided by P2 also. So we have two formulas for work done in case of isothermal process. Moving on, we will solve problem based on the same. Calculate the work done when 5 moles of an ideal gas at 300 K are expanded isothermally from initial pressure of 4 multiplied by 10 to the power 5 Pascal to final pressure of 1 multiplied by 10 to the power 5 Pascal against a constant external pressure of 10 to the power 5 Pascal. This is your question. Is it clear? Now, let me start by considering what is given in the question. 5 moles is given, so let me consider n is equal to 5. N is equal to 5. Temperature is given, T can be taken as 300 Kelvin. Initial pressure and final pressure is given. P1 is going to be the initial pressure, it is 4 multiplied by 10 to the power 5 pascals, and P2 is going to be the final pressure, it is going to be 10 multiplied by 5 pascals. Same thing. Right? Anything else is given in the question? No, right? I can consider the value of R as 8.314. This is going to be a constant. Now, I have to find out the work done. Work done is given by two formulas. Those are 2.303 multiplied by nRT log V2 divided by V1 or P1 divided by P2. In this problem, I will be using the second one because initial pressure and final pressure is being given. 2.303 nRT log P1 divided by P2. This is going to be the formula. Substituting the same W, which is going to be the work done, is 2.303. You can use your calculators. 5 is going to be n is going to be equal to 5 multiplied by 8.31 multiplied by 300 multiplied by log of P1 divided by P2. P1 is going to be 4 multiplied by 10 to the power 5. So I can write this as 4. 10 to the power 5 is going to be getting cancelled. Divided by yes. Now, substituting all the values, you will be getting 2.303 multiplied by 8.31 multiplied by 5 multiplied by 300 can be written as 1500 multiplied by what is going to be log of 4? Log 4. Can anyone find out? What is going to be the log of 4? Point 6. Yes, around zero point 0.6 you will be getting. So you will be getting W as when you multiply everything, you will be getting the value as 17,224.13 joules. This will be your final answer, or you can write this as work done is 17.22. Yes, 22 is enough kilojoules. This will be your final answer. So I can write zero point 0.6 over here. Is it clear? Now we are going to take one more problem. Calculate the work done in joules when zero point 0.2 mole of ideal gas at 300 K expands isothermally and reversibly from an initial volume of 2.5 liters to final volume of 25 liters. Let me start by writing whatever is given in the question. N is being given in the question. So let me take N as 0.2. Temperature is given. T is equal to 300 K. Initial volume and in final volume have been given. V1 is going to be 2.5 liters. Final volume is going to be 25 liters. R can be taken as 8.31. 8.31. Work done. In case of an isothermal process, we have two formulas: 2.303 nRT log V2 divided by V1 or P1 divided by P2. In this case, final and initial volume have been given, so I should be using the first formula. Yes, right? Now, considering the same, I will be getting over here work done is equal to 2.303 nRT log V2 divided by V1 in this case. So it is going to be W 2.303 multiplied by zero point 0.2 multiplied by 8.31 multiplied by 300 multiplied by log of V2 is going to be 25 divided by 2.5, which is nothing but log of 10. Yes, you will be getting log of 10, right? So 2.303 multiplied by zero point 0.2 multiplied by 8.31 multiplied by 300 multiplied by log of When you cancel this, you will be getting the answer as 10. The value of 10 log 10 is 1, so you can substitute the same. W is going to be 2.303 multiplied by zero point 0.2 multiplied by 8.31 multiplied by 300. So the value you should be getting approximately equal to 115 joules, right? Approximately you will be getting 115 joules. Is that clear?